Okay, so some logistical things to just recall. So on Thursday, which is I think October 26th, we have 2 hours in class. However, on Tuesday, October 29th to 30. 31st, maybe? 31st. Yeah, right. Yeah, 31st. Yeah. So the 31st. Yeah, we have regular, but yeah, this will be online because I will be traveling, but I will send you the link. So I'll just give the. Other than that, everything is the usual. So and also, yeah, I will. So homework 2, I have it ready. I will just post that today, just after class. So similar. And then, but then the other thing is there will be a final project, as I mentioned before, and for that, we will meet sometime in November to discuss topics. I'll send you a list of topics, but yeah, maybe I think good time since the classical since the reading week for arts and science is November 6 to 10. So maybe we can meet on November 13th, which is a Monday after that. And during office hours or something, and discuss a little bit to decide which project you want. Okay, anyways, these are just boring stuff. Are there any questions about the administrative part? Okay, so if not, we can go back and start and recall what we proved last time. So last time we proved the convergence to the boundary. By the way, I updated the notes, so now there is I think there are all the details of the proof that I said last time. So the convergence to the boundary of a random walk on SL2R. And so first of all, today I want to give a kind of cool application of this theorem. So, okay, let's recall what the theorem is, which is due to first word. And it's the following. You start with mu, a non-elementary measure on SL2R, or on a countable subgroup of SL2R. So this is all countable. And you should remember what does non-elementary mean? Anybody remember?
It takes a finite set of points.
It does not fix a finite set of points. And it's not contained in, it's not compact. It's not contained in the compact. Yeah, that's right. So then for any point O in the disk, for almost every sample path Wn, sample path, the limit, that's n goes to infinity of Wn, O exists, and it's a point on the boundary of the disk. So again, the picture that we've drawn so many times already, like that. So now I want to give a kind of a cool application of this theorem to a geometric problem, completely geometric problem. Application to barycentric subdivision. Just to just to see how we can interpret the classical geometric problem in terms of random walks and groups. So the problem is like this. So you start with the triangle in the plane. And now I can, whenever you have a triangle in the plane, you can draw the medians like that.
Are you're thinking like an R2 plane or like an
R2, yes. Okay. So yeah, in a Euclidean plane, yes. So, and now, okay, so yeah, you take the medians like we did in high school. That, and then we have a die. We throw a die. There's 6 faces. There's 6 triangles. So we pick one of them randomly. So start with a triangle, T0. Then you draw barycentric subdivision. And you pick one of the 6 resulting small triangles, randomly. And then, of course, you probably know what we're doing next. We pick one. Yeah, so let's say T1. And then T1, again, we can divide in 6 triangles. And again, we toss this die, and there's 6 possibilities, and we pick one, and so forth. Okay? And so repeat, obtaining a sequence Tn of nested triangles. Okay? And so the question is, what does the, on average or asymptotically, what does this triangle look like? What's the shape? Of generic triangle like that. So it turns out that from the convergence theorem of Fürstenberg, we can prove the following. So of course, whenever you have a triangle, well, of course, these triangles get smaller and smaller in diameter. But to look at the shape, well, we want to normalize, right? So we rescale to get, again, a triangle that has the same diameter, right? But then what it turns out is that the triangle gets, basically the triangle gets thinner and thinner, like gets more and more degenerate. So the theorem that you can get is the following. And in this situation, in probability, you have that the area of delta n, or Tn, sorry, divided by the diameter of Tn squared, the normal, yeah, you want to normalize like that, right? The area scales like length squared. So you take the diameter squared to normalize it. In fact, tends to 0. So you can try yourself whenever you do subdivision. Basically, you have to be extremely careful, like extremely lucky for this triangle to still look somewhat fat. I mean, this triangle eventually gets very thin like that. It's kind of intuitive. If you try from an equilateral triangle, right, and then you take the subdivision, you can see what happens. So okay, maybe there is another proof of this, but it's fun to get it from a convergence result from SL to R. So a priori, it's not completely obvious that there is a relation.
How can a triangle not get slim? I'm just curious. Like, which is it? Is there a clear situation where the triangle doesn't get slim? Like, is that I'm maybe confused.
Well, I think if you take always the fattest one, you know, maybe you can delay this process. Yeah, I'm not sure whether maybe all sequences get slim. It's possible, but I haven't tried.
Thanks.
I think if you start from the equilateral case, it's true. But if you just have a general case, you see maybe this one, for instance, this one looks, yeah, it does not look skinny. So if you do it carefully, I think you can find sequences that are.
I see. Okay. Yeah. Thanks.
But it's true. I mean, yeah. I don't know. I mean, this is not really a very deep question that I thought a lot about. But I just. So I don't know exactly what happens. But this is a kind of neat application. So what's the idea? So what's the proof of this? So the proof of this is to look at, to be fancy, we could call it the moduli space of triangle. What does it mean? Well, it means that, you see, okay, I have a triangle in the plane, and you want to study its aspect ratio, so you can normalize it. So of course, what can you do? Well, you can rescale, and you can rotate. So this, of course, it does not change the shape. So up to rotate and rescale, what can we do? We can assume that two vertices, sorry, are at 0 and 1 in, say, the complex. Right? So we can assume that this is at 0 and this is at 1. Right? And also up to rotating, relabeling, we can assume that the third vertex has positive imaginary part, if we think of it as being in a complex plane. Up to relabeling, right? Relabeling sides and the third vertex is at a point that we will call tau, with the imaginary part of tau strictly positive. And that so in that sense, you could say that the modular space of all such triangles is parameterized by the upper half plane. Right? Why? Because any triangle can be represented in such form. And basically, yeah, up to rotation and rescaling. So if you have another point, tau 1, where this is not the same up to rotation and rescaling. Okay, so this is the space, and then we need group action. And so the group action is given by barycentric subdivision. So the group action given by barycentric subdivision. Why not? Why? Well, because you see, barycentric subdivision starts with a triangle, let's call it T0, and it produces 6 triangles, T1, T2, T3, T4, T5, T6. Okay. So, you know, these are like T1, T2, T3, T4, T5, T6. And now, what are those? Right? So as an exercise, maybe let's compute what is T1. Okay. So again, if we start with a triangle which is in normal form, 0, 1, tau, and now we do the barycentric subdivision, okay, so T1 is this one. And what is the normal form of this? Well, let's think about it. So this is 1/2. And what is this coordinate? So this is between 1/2 and tau, 1/3 of the way, right? And so what is it? It's right. What is it? 1/6 plus 2/3 tau. So tau 1 is represented by the class. Let's say the class of tau 1 is the class of 0, 1/2, 1/2 plus 2 tau over 3. But of course, this is not quite in normal form. To make it into normal form, we have to rescale it by 1/2 to make it to make this side to be 1. Right? And so this is the same as the class of 0, 1, and then this is 1 plus what? Plus, I guess, 4 tau over 3.
Why was that 1/2 and then 1/6?
What about it?
For the plus 2, like 1/2 plus 2 tau over 3.
So this is tau. This is 1/2, right? So we're taking the convex combination between 1/2. Why did I write one? Oh, I should write 1/6, right? Yeah, so it's 1/2 times 1/3 plus, yeah, plus tau times 2/3. Yeah, so it's 1/6. Okay, good. Okay. So then this is 1/2, 1/3. Yeah. All right. Okay, so you see that this triangle as a point in the plane. So the map T1 is a map. So there is an associated map. Let's call it G1 from H to H that represents the first choice of the subdivision. So the map is tau goes to this one. So yeah, 1 plus 4 tau over 3. So you can see that this is in the is in a group of isometries of the upper half plane, right? So okay, we can write it, right? So this is okay as a matrix. Okay, this is 4, 1, 0, 3, for instance. the right? Let's see. Right. Yeah, so this is okay. This of course has determinant 12, so it's not quite normalized correctly. We if we want to really write it in a SL2R, we have to just normalize. But okay, we can normalize it. So this is, how do we normalize this? Well, yeah, we need to what, divide by right. So this is what, this is 1/3 plus 4/3 tau. So also we can also represent it as 4/3 plus 1/3, like this. And then we have to divide by 2 square root of 3 to say to write it in SL2R. But okay, it's fine. I mean, this is the yeah. Right. So how do we write this in SL2R? We divide by, yeah. We divide by 2 square root of 3, I think. So this is 2 over square root of 3. Yeah, 1/3, that's square root of 3 over 2. 0 square root of 3 over 6. Anyways, yeah, that's it doesn't really matter what this is a this is in a group of isometries, of course, for sure, of H. So okay, so this is one example. Now you can convince yourself that all the other ones also, yeah, also are in the same yeah, the same way. So there are 6 operations. There are 6. There are G1, G2, G6, which are isometries of H, such that, yeah, such that Gi of tau, the class of Gi of tau is the class of Pi. Yeah, basically you have to flip the vertices, so you have to do the computation, but you get these other things. Any questions? Okay, good. So now, yeah, now we see that if we take randomly 1 out of 6 such things, is the same as taking randomly one of these 6 isometries. Okay. And so now if we consider a random sequence, the ice, well, basically, we know that the class of the nth would be what? Would be the class of a composition of this random mass. In fact, here we do the composition from the left. So this is what? This would be like G I n minus 1, Gi1 of tau. And so now we can see that if we know what happens to this point in the plane, we can tell us, we can figure out what happens to the shape of this triangle. So why is it the case? So what happens? So we have to check. So first of all, we need to check. So the measure mu is the measure 1/6 delta at GIs from I equals 1 to 6 on group of isometries of H. Yes, of course. So we have to, so first of all, okay, so we need to check. So this is something you can check by writing down the maps. Concretely, we need to check that the group generated by G1, G6 is non-elementary. Now this one requires a little bit of checking. But once we have that, then we can apply Furstenberg's theorem. So what does Furstenberg's theorem tell us? Yeah.
Furstenberg's theorem don't multiply by the right.
Correct.
So is that a problem?
We'll see. Correct. So so what does, yeah, you're right. So Furstenberg says that if you multiply the other way around, yeah, so GI1, GI2, GIN of tau, like this, converges to some point psi on the boundary of H, almost surely. In particular, what does it mean to converge to the boundary of H? So if you look at the aspect ratio, right? So if this is 0 and this is 1, well, what is the aspect ratio? Well, this is H, right? So if it converges to any point in the boundary of H, except at infinity, which, okay, in fact, even at infinity, because if it converges at infinity, the triangle also will have a very skewed aspect ratio. But certainly if it converges here, like you see that so if this is the Wn of tau, you see that the area of Tn divided by the diameter of Tn squared, well, the area of this triangle is just the imaginary part of this guy divided by 2. This would be 1/2. Okay, the diameter is whatever it is, but yeah, the diameter of this is basically 1. Yeah, so the area of this would be, yeah, so this is like the imaginary part, 1/2 of the imaginary part of Wn tau. So if we multiply the elements this way, then you see that this walk goes to the boundary. This shows that this is going to 0. Now there is one issue, which is we are multiplying the other way around. And however, so here is the observation. So that's why I did not write almost surely. So this is all true almost surely and in probability. But in probability, it doesn't matter whether you're multiplying one way or the other. So note the following, that the walk, so if you do G1, G2, Gn, and Gn, Gn minus 1, G2, G1, so these walks have the same distribution. And that's because, yeah, I mean, you're just taking, you see, this n elements, you're taking all possible choices of all the elements, and you take n tuples of them. So it doesn't matter whether you multiply on the right or on the left. So the probability that this equals certain g is the same as the probability that this equals certain g. And so since the conversion we care about is not almost surely, is not clear, but in probability, then in probability, you get the same. So we also, so basically what we also have is that the imaginary part, if you want, of this one, G1, of the walk multiplied in the other direction, G1 of tau, converges to 0 in probability. In fact, because this guy goes to the boundary of the plane, we also showed that the hidden measure is not atomic, so it cannot be concentrated at infinity. So that's not. I recall that the hidden measure. Not atomic. So not supported at infinity. So that's it. So basically, we can show that by just this argument, by looking at the action on the space of all possible triangles, which turns out to be isomorphic to the upper half plane, and the fact that this barycentric subdivision acts by isometries, by Möbius transformations, we can relate the random barycentric subdivision with the random walk on PSO. Yeah, anyways, yeah. So I don't know. I just think this proof is just really cool, but I don't know what you guys think. I don't see much excitement in the room, but that's fine. So any questions?
Question.
Yeah.
How hard is to show it's not elementary?
Well, we did show.
This
Oh, that's one. Yeah, it's a good question. I don't think it's really hard. I tried it once. I mean, yeah, everything is divided by 6. So I think that helps. But yeah, no, this is a good question. Other questions? Okay, good. So Okay, so now we can go to the next topic, which is harmonic functions.
Guess I'm wondering.
Yeah.
Are there more elementary ways to prove that this area divided by diameter squared goes to 0?
I don't know. That's a good question. You could try. Again, maybe it's true for every sequence. Okay. So in a yeah, so we know what a harmonic function is maybe in Rn. Right? So in Rn or R2, let's say. Well, a function U so from an open set into R is harmonic if the Laplacian is it. Now, if we're in the discrete setting, we don't have a differential operator like this, but we have a version of it which is discrete. Also, another important point is that you can note that, well, you can, another way to say a function is harmonic is to say it satisfies the mean value property. So U satisfies mean value property. So what does the mean value property say?
It's average on a ball.
Yeah, that's right. So if you take U at a point x naught, right? This is the same as the average on a ball or on a sphere, right? So maybe let's say on a sphere, 1/2 pi, the integral of U of x naught plus R e to the I theta, right? D theta, something like this. Divided by no, we're just doing on the sphere, not on the ball.
The area of the sphere 2 pi r.
The area, yeah, of the sphere. Let's see. Yeah, no, I understand what you're saying. Yeah, it depends on what is the measure that we're looking at, right? So but let's say if U is constant. No, but I just integrate over d theta, so, right? So if U is constant, this is 2 pi. So yeah, that's good. Right, so this is x naught, and then this is x naught plus R to the I. Okay, so this property can be easily discretized for a function on a graph. Right, so if we have, so let gamma be a graph, then f from gamma to R is harmonic. If what? Well, if f of x is 1 over the degree of x divided by the sum of f of y, where y is a neighborhood of x. So this is standard definition of function on a graph. So the graph could be, well, any graph. Something like this. So if you have a point x and it has a bunch of neighbors, you want the function to be the average of the function at its neighbors. Then of course it depends. So this graph might be interpreted as having a boundary or not. So this depends a little bit on what problem you're looking at. So if you think of this as not having boundary, well then yeah, then you have this for every x. But sometimes you also want to impose this condition only for every x in gamma minus the boundary of gamma. So because sometimes you have a boundary condition, so maybe so maybe you assume that this is the boundary of the graph. And so you're asking whether you can prescribe the function at the boundary. Once you have the function prescribed at the boundary nodes, then you can ask whether the function extends at the interior as a harmonic function. That's a classical Dirichlet type problem. And for groups, we can do something similar. So we can say that, so if you have G and mu, a measured group, so a group with a measure, then f from G R is mu harmonic. So this mu tells us how to do the average. If, again, so if f of G is what? Is the average of the neighbors of G. And if this is a group, every neighbor is G times H. So you think of this mu as giving a weight on the neighbors. And then, okay, if you just have a general group, you should take the integral with respect to H for every G. So literally, this H tells us how to go to the neighbors, to the neighbor of G. So of course, sometimes most often we're going to look at countable groups. So for countable group, you can replace the integral by sum. So if G is countable, you just say that f of G is the sum of f of GH mu H, H and G for every G.
But here you're not really necessarily assuming that H is a generating element or anything, right?
No. So mu is any measure on G. So yeah, of course, this weight could be 0 for many values of H. Yeah, it doesn't matter. Mu is a weight on G, so any probability measure on G. So could be supported on generating set, could be supported on all of G, could be supported to not on just the identity. That's cool. For instance, if mu is supported only on the identity, well, every function is harmonic. Of course, it's a pretty stupid example. So that's why it's really important to say it's harmonic with respect to which. And again, so maybe the easiest example would be if G is you know, is the 2, for instance, and mu is the classical is the classical lattice, then you get the classical notion of harmonic function on two-dimensional lattice. Because in this case, the H is just literally tells you to go up, down, left, and right with probability 1/4. And so you're taking just literally the average. So that's the easiest. Okay, so of course, so we also recall that constant functions are always harmonic. As this trivial fact. So constant functions are harmonic. And the question is, are there others? And we denote as H infinity. So there's 2 classes of harmonic functions that we care about is H infinity G mu, which is F from G to R, mu harmonic and bounded. And then positive harmonic function H plus G mu, which is F from G to R plus mu harmonic. So they're positive.
Giulio?
Yeah.
When you brought up the question of extending a function on the boundary to the inside, it reminded me of sort of the Ponzi scheme. Is there a relationship between admitting a Ponzi scheme and a major and a
absolutely yes. So yeah, we will see. So yeah, of course, amenability is very closely related to this whole story. So we start with finite graphs now, but then with infinite graphs, it's exactly what you said. So right. So yeah. So anyways, so these are the 2 classes of spaces that we're interested in, and again, both of them, of course, contain the constant functions. As the question is, do they contain others? Now let's also look at the maximum principle that we also have. As we probably know, so if we have a harmonic function in the classical sense, we have the maximum principle. Right? So the maximum principle says that if you have a function and it attains a maximum and a point, and it's harmonic, the maximum cannot be in the interior of the domain, because if it's in the interior of the domain, then the function has to be constant. So for graphs, there is a similar thing, and also for groups. So literally the same is true. So if from gamma to R, so is harmonic and achieves its maximum in the interior of gamma, then F is constant. And again, I stated for in this setting, I stated for a graph, gamma, a graph. So I assume that, yeah, we have a graph, and we label certain nodes as its boundary and the remainder as the interior. So That's our picture. So the proof is similar, of course, to the classical one. So if, again, gamma has to be connected off. Otherwise, it can be constant on one connected component. So obviously, if f of x is maximal, well, you write f of x equals 1 over the x sum of fy. That. And then since it's maximal, everything is less than f of x. But of course, this is just also f of x.
What's the measure here? What's mu?
No, yeah. So here, so I wrote it for graphs. So here, but we could also write it for groups. It's the same. So here, so for graphs, I just mean that I'm taking the average with respect to the neighbors. For groups, you're taking the average using mu. So this it's exactly the same proof. So yeah, of course, it's different, right? So because for groups, if you have a homogeneity with respect to the fact that every vertex looks the same locally because it's a group. Like here is slightly more general because you can have different degrees of different vertices can be different. So that's why I write it in this version, which is slightly more general. Yeah. So, anyways, so we know this. So this implies, of course, that f of y has to be equal to f of x for every y neighbor to x. And so by the fact that gamma is connected, we know that f is constant. So as a corollary, indeed, if you have a function on a finite group, so if f is mu harmonic on a finite group, well, then f has to be constant. And the reason is, of course, because if the group is finite and the function is bounded and it has a maximum,
Is there some sort of a generalization of this corollary where the finite group G is compact and it has a maximum? So,
yeah, if you have a compact Lie group, you can replace the sum by the integral. Yeah, it's the same. Yeah, because you still have the instead of the sum, you have the integral. But if the integral of f is less or equal than the integral of g, but f is bigger than g, then f equals g almost everywhere. Right. So here, of course, yeah. So the proof of this is just that since g is finite, every harmonic function is bounded. And attains its maximum. Also, this is a group, so there is no boundary. Like every node is an interior node because it's a group, so everything is homogeneous. Okay, so that's sort of somewhat expected. Now, again, so we look at the problem of harmonic extension. Let's see what time. Yeah, it's almost time for a break. So yeah, so let me just state the problem, and then so if gamma is a graph with boundary some set of nodes given, and if given a function phi from the boundary of gamma into R, is there f from gamma from all nodes such that harmonic such that f restricted to the boundary of gamma is like phi.
So we don't know what a boundary is yet. This is just a vague thing so far, right? Is that?
Yeah, I'm just saying, like in basically in a graph situation, you can have, yeah, whenever you have a graph, you can have a subset of the nodes that you declare to be the boundary. So what makes most sense, it depends on the situation, but this question, in fact, always makes sense. For a group where we will not have a boundary, the boundary will not be inside the group, will be at infinity. So
okay, so the boundary is allowed to be points in gamma itself, you're saying, in general here.
In this setting, yes. In this setting, yes.
Okay, thanks.
Yeah. Okay, good. So maybe let's take a break till 11:10, and we can reconvene. So I guess we can get started again. So we just mentioned the problem of harmonic extension, and we'll see how to solve it in the finite case first. And then in the infinite case, well, that's a hard problem. So this will be, a significant part of the course. But for the finite case, it's actually fine. I mean, basically, it can always be solved. So basically, the theorem is if gamma is finite, then for any function, any function on the boundary of gamma, which again is a fairly arbitrary subset that you of nodes that you just declare to be the boundary. Because in this case, it's this orange ones, but basically just that. So then you find that any function on the boundary can be extended to a harmonic function on gamma.
Okay, Giulio, I'm a bit confused because I thought the only possible harmonic functions on a finite set from the previous corollary are the constant ones. So what am I?
So there is a difference between problem with boundary or without boundary, right? So this is the problem with boundary, which is more general. So we have a graph gamma, and we consider some subset of the vertices, and we call it boundary, right? And now the problem becomes, if I have a function on the boundary, can I extend it to a harmonic function on gamma?
Okay, so basically here the boundary allows for some error so that
That's right. That's right. In the previous thing I said, the boundary was empty. Then indeed, if the boundary is empty, then on a finite any graph which has empty boundary, then the only harmonic functions are constant. Yeah, exactly.
Got it. Thanks.
Because the harmonicity you can check only, by definition, only on the interior of the graph. So if you check, if the boundary is empty, you check it everywhere, and that's stronger. Yeah. Okay. So the proof of this is kind of neat. It has two parts. So it has an existence part and a uniqueness part. So again, so in this picture, let's assume that this orange nodes are the boundary nodes, and we fix any function there. And when we want to say, okay, can we extend it to the blue ones? Well, there are many ways to think about it. Of course, you see that this harmonic property is a linear combination of of the function and the neighboring nodes. So of course you can think of phi as the function which is the boundary value from the boundary gamma to R. Okay, this of course you can think of this as an element of the vector space R to the boundary of gamma, and then F, which is the target function, which is the function on the whole graph, could be thought of as an element in R, the gamma. So, and you can write, the harmonic for each y, for each node y inside gamma, there is, so the harmonic condition. Yeah, harmonic condition is one linear condition. So it's one linear condition. So basically, you want to figure out whether this becomes a linear system of equations. You're given this many variables, and you have however many conditions as the number of the interior. So the number of conditions is, of course, the cardinality of gamma minus the boundary, which coincidentally is the same as the number of variables that you have, because you want to guess indeed the number, the function at each interior point, because you already have the function at the boundary points. So you have to find this. So the number of variables, again, is again the cardinality of gamma minus. So in a way, you would expect that there is unique solution. So in fact, there is, but of course it's not obvious. So we can do a probabilistic proof. So we could do linear algebra proof as well, but let's look at a probabilistic proof. So the probabilistic proof goes as follows. You want to define the value of a function at a node. So let's start with the node x. And the way we define the value of a function is we run around the walk on this graph by taking all, you see, at each step, you take an uniform probability on the neighbors. So it's a stream around the walk. So here you have two choices. You take each of the choices with probability 1/2. And here you would have three choices. And you take each of them with probability 1/3. And then if you hit the boundary, you stop. and you record the function at the boundary because you already have the function. Okay? So given X, an interior node, you define, yes, you define that and Markov chain, a simple run a walk. On gamma, and that stops when you hit the boundary. And with probability 1, you will hit the boundary. Right. This is something you have to think about, but if it's a finite graph. Okay, and so
the sample space here is all possible paths that start at X and wind up at a boundary point?
Yeah, exactly. The sample space is all the possible paths that start at X. And in fact, yeah, the ones that don't hit the boundary have measure 0. And so you just have the ones eventually, when you're in the boundary, you stop. And so you just take the value of the function, the limiting value of the function or at this. So you define f of x as what? As the limit as time goes to infinity of phi of Zn. So phi is a function on the boundary. At some point, you're going to stop and hit in the boundary and associate that value. And so the claim is that then f is harmonic. That's what we want to claim. And that's somehow obvious. I mean, like it just sort of goes through the you go through the definitions basically. So f of x is the expectation. The expectation. Sorry. So the expectation of the limit as n goes to infinity of phi of Zn. But of course, you can end up at different points on the boundary. And so, of course, you can, since this is a limit, you can take it at Zn plus 1. That will be the same. So this is the expectation of the limit at n goes to infinity of phi of Zn plus 1. And the idea is that you condition and what happens at the first step. Right. So which one? This one? Oh, just because this is a limit.
Oh yeah.
So you just replace n plus n. Yeah. So you just replace n with n plus 1. Just go. Yeah. And so, basically what you want to say is that you see the first step, right? So you have Z0, which is X, and then you have Z1, whatever it is, and then you do Zn plus 1, so you have n steps going on from there. And so the thing is, you have the sum of the probabilities of, so you're conditioning on the first one. And so so this is what? well, this is the sum of, the expectation of limit of Zn given that Z0 is Y times the probability the Z1, if you want to say. Right. So this is the probability at step where the first step is Y. And of course, Y has to be a neighbor of X because otherwise the first step was not going to be Y. And then once, yeah, you can usually you can start like that. Yeah, this is literally, yeah, if you want to write another step, say like this. But then then this is Markov process. If you start at Y, then you get. So this is the same as what? As the same as the sum from Y neighbors of X. And this is F of Y. And then the probability, yeah, times the probability that Z1 equals Y. So that's okay. In fact, you see already that this proof doesn't really matter whether you're taking the uniform, the simple random walk, or you take any other way of taking the neighbors at each step, because it's exactly the same proof. In this case, literally you get 1 over the degree of X. This would be the probability that you hit Y, but otherwise. So it's just that the limit exists. And in this case, the limit is easy to show it exists because everything is finite. And otherwise, it's much harder. And maybe the limit sometimes is not. Okay, so now we also want to show the uniqueness. And the uniqueness also follows from some very important principle, which is the maximum principle. Okay, so suppose that F1 and F2 are harmonic extensions of the same phi. So these are two functions that are harmonic inside, and they are the same on the boundary. Right? Now, if we take G, which is F1 minus F2, of course, this is harmonic. Again, on gamma minus the boundary. And then G restricted to the boundary, well, is 0. Yeah. So now, if I set the boundary values to 0, what is the value of the harmonic function inside? And the answer is 0. And why is that? This is by the maximum principle. So by the maximum principle, well, you see G is 0 on the boundary. So G, this is finite. So the maximum of G also has to be attained on the boundary. Right? Occurs on the boundary of gamma. So the max of G on gamma is 0. But of course, negative G is also harmonic. So for the same reason, so the max of negative G also occurs on the boundary. And so the max of negative G is also 0. So again, this is a very important property. Like this rigidity comes from the maximum principle. Again, this is almost always in complex analysis, harmonic analysis, any of these fields, the rigidity statement comes from the maximum principle of version. There are not so many actually tools that tell us to prove this rigidity. Okay, so that this we get the G will be 0, and so this will, of course, would be. Okay, so that's for finite graphs. So we are in a very good shape. Whenever you have this boundary condition, you can immediately extend, and there is a unique way to extend it.
Okay, so just before we start the next thing, so so in this proof, like you wanted a harmonic function and you define it to be the expected value of the boundary. Suppose like conversely that you have a group and you have a mu stationary measure on it. Is there a way that you can always interpret this mu stationary measure as some sort of an expected value on some boundary, or this is just maybe in the finite case, I guess?
So you have a stationary measure.
Yeah, so you have a stationary measure.
Infinity, not on the group, right?
No, you have it on the group. Suppose you have it on the group.
Right.
And I wonder if you can interpret it as some sort of an expected value, some average that's taken place on the boundary rather.
But what is the boundary here?
Yeah, that's a good question. I don't know. Yeah. Yeah. Yeah, no, the question was vague to start with. So
the idea of defining boundary values by taking the limit along subsequent along a random walk. I mean, this is still going to be the case for infinite groups when the boundary is at infinity. So in fact, we already looked at it last time in SL2R. We already looked at this martingale that you get, and from averaging, and you're taking the limit, and the limit exists by the martingale convergence theorem. So that part still is true. Yeah, usually you don't have harmonic, you don't have stationary measures on the group itself. That's the thing.
Okay, thanks.
Unless because it has to be like, if the group is infinite, this would not be a measure. It would be an infinite measure. Like the Haar measure would be an example, but that cannot be probability measure unless the group is very, very special, like it's finite or compact. Okay, other questions, comments? Okay, good. So now we let's look at a couple of examples of harmonic functions on infinite groups. It will tell us that more interesting things happen. Well, let's first start with something maybe not so interesting. So, okay, so first of all, so if you look at harmonic functions on abelian groups, okay, so on Z. So first of all, we probably can do the exercise that if you have yeah, if you have just a simple random walk on Z, so delta plus 1 plus delta minus 1, right, and so f from Z to R harmonic, what are the options here? Well, so what does it mean to be a harmonic? Well, it just means that f of n is 1/2 f of n minus plus 1 plus f of n minus 1. So this is fairly easy. So what are the solutions to this? So fn plus 1 minus f of n equals fn minus f of n minus 1, right? So if we set this, we call this B, what are the solutions? Yeah, right. So if you sum this, you get that, for instance, right. So f of n would be the sum of f of k plus 1 minus f of k, for instance, from k equals 0 to n minus 1, like this. So each of this is B. So this is right. So f of n minus f of n minus f of 0. So this is n times B. And so if we set A to be f of 0, well, f of n is A plus Bn. So if we look at all harmonic functions, there are more than constants. There are also the linear functions. But yeah, so then it depends on whether we want constant, if we want bounded functions, and if we want positive functions. So the bounded functions are what? So if B is non-zero, then this function is not bounded, right? So these are only constants. So f, yeah, so constant. And if you do H plus, so if you look at positive functions, also what happens? Well, again, if B is positive, then this becomes positive for n positive and negative for n negative. And vice versa if B is negative. So again, it's never going to be positive all the time. So this is, again, there are no functions like that. So here's another example, though.
Are they supposed to be the same?
Well, not always. That's the thing.
Should this be?
Oh, these are positive. Oh, sorry. Yeah, this is just positive. So in this case, they're basically the same in the sense of, yeah. But in general, well, they do not be the same. And in fact, yeah, one could be just a constant, but the other could be also not the non-constants. Okay. But okay, so now let's look at the generalization of this, which seems very tame, which is, what if we do random walk with drift on Z? So instead of 1/2, 1/2, we do bias. Okay? So for instance, we do mu is delta minus 1 plus q times delta plus 1. over 1 plus q. So q is some parameter. So this is also, again, on Z. Okay. So now, are there functions that are harmonic here, and are they interesting? Let's see, right? So what do we want here? Here we want f of n equals 1 over 1 plus q f of n minus 1 plus q over 1 plus q f of n plus 1. So what is the solution of this recurrent? So so again, let's start. So we have f of 0, let's call in f of 1. Well, let's call this A and this is B. And then obviously there's only another degree of freedom, because once you know 2 of those, then we can do the other ones, right? So for instance, you would have that f of 2, right? So f of 1 is f of 0 divided by 1 plus q plus q over 1 plus q f of 2. Okay. So in general, we can get f of n plus 1 out of those two. So f of n minus f of n minus 1 over q plus 1 equals q over 1 plus q f of n plus 1. So f of n plus 1 is what? Is 1 plus q over q f of n minus right? So we divide by q, I guess. 1 over q f of n minus. I think that's okay. So let's see. So again, f of n plus 1 is 1 plus q over q times f of n minus 1 over q f of n minus 1. So f of 2, for instance, is what? Is b 1 plus q over q minus a over q. Let's see. So this is 1 plus 1 over q, 1 plus q to the minus 1. This is a q to the minus 1. This is b plus b minus a q to the minus 1. So in general, maybe we can write this like that. We can write it as what? As f of n plus q to the minus 1 f of n minus f of n minus 1. Can you see? Can you see the recurrence now? Yep.
If you divide or subtract f n from both sides.
That's right.
The increment increases by.
That's right. So f of n plus 1 minus f of n is equal to q inverse f of n minus f of n minus 1. Yeah, so the increment is every time multiplied by 1 over q, right? That's right. And so if you keep doing that, right? So if you go to f of let's say f of 1 minus f of 0, right? This you have to multiply by q to the minus n minus 1. Good.
Now q minus n.
I think n. So if you take the sum of these two, so this is n plus 1, right? So you're saying it should be minus n, yeah, maybe. So yeah, you have maybe minus n. Right. In any case, yeah, this is an exercise, but since the class is not really very energetic, let's see. So let's say, so it turns out that f of n equals q to the minus n, supposed to be a solution. Let's check if this is the case. So what do we need to check, right? So we need to check this one. So this is q to the minus n equals q to the minus n plus 1 plus q and q to the minus n minus 1 divided by 1 plus q. And so, right, so you see that this one simplifies with that. So this is q to the minus n times q plus 1 times divided by q plus 1. Okay. So it turns out that these are the two solutions. So the two solutions are the following. So if we forget about the boundedness or anything, so just h of z with this measure, which depends on q, well, we have the constants. And then we have q to the minus n. So this is times, obviously you have all the linear combinations. So you have q plus b times q to the minus n, such that a and b are in R. And now, of course, we can guess. I mean, we can figure out exactly which ones are positive and which ones are bounded. Right. So in fact, it turns out that the bounded ones, are there any bounded ones? Right, so if you look at this measure mu q, Let's see if there's any bounded ones out of those. Yeah, definitely constant ones, but the other ones are not, because if this n is in z, so it doesn't matter, right? This either for n very positive or n very negative, this always will blow up to infinity, right? So these are just constants. Yeah. So now the other thing is, what about the positive ones? Well, the positive ones, if we assume A and B are positive, for instance, then we're in good shape. So these are f of n equals A plus B e to the minus n, where A is non-negative and B non-negative. These are all possible, are all good solutions. Okay, so you see that already here there's a difference. Now, another reason why I really like this example, not so much for sake of just doing an exercise, but the thing about this is that you can start with this and you get a harmonic function on a tree. So what about a Q-regular tree? Right, so for instance, for Q equals 4, you get the usual tree group. So let's take TQ, so the Q-regular tree, and let's take mu, which gave us the simple Ranois. So the uniform measure on the neighbors of the Q neighbors. So what is kind of cool, maybe we can, we can see it next time. So because we don't have too much time, but so what it turns out is that by modifying this example, so there are bounded non-constant functions on this one. Yeah. So even if this seems to be similar to the square grid, in fact, it's very different. And the trick, you have to think about it a little bit, but the trick is to modify this example here. So maybe let me just say, what is the main idea? The main idea is that you think of this tree like that. So you let's say you fix an edge of the tree. So the tree is split in two parts. So we fix an edge. So we sort of cut the tree in two parts. And then we first construct a harmonic function on the right-hand side of the tree. And the way to do that is to look at the distance from this point I call it X. And we take Q, Q to the minus distance. Yeah, the distance between X and this. So Q to the minus distance, let's call this Z, and X and Z. So at each step, so for instance, here you have 1. Here you would have Q to the minus 1. You have Q to the minus 2. Here you have Q to the minus 2. And then you have another Q to the minus 2. So at each neighborhood on the right-hand side, so at each neighborhood looks like this. On the right-hand side, each neighborhood looks like this, Q to the minus n. On the left-hand side, there's Q to the minus n minus 1. And then you have the children, Q to the minus n plus 1, Q to the minus n plus 1, Q to the minus n plus 1. And now you can check that this is harmonic at all the nodes to the right. Right? Because how many nodes there are? Well, there are Q minus 1 of nodes. So we want to check that Q to the minus n is what? Is, well, you have Q minus 1 nodes to the right times Q to the minus n plus 1 plus the nodes to the left, which has value Q to the n minus 1. And then the total valence is Q. Let's see, is it Q or Q plus 1? We have to. So Q to the minus n is simplifies. And let's see if it's true. Check that. Let's see, it's literally like that. So you have Q to the minus n that simplifies, and you're left with Q to the Q minus 1 times 1 over Q, minus 1 plus Q divided by Q. That's it. So this is 1. Minus Q to the minus 1 plus Q. No, it's not quite that. There's going to be Q plus 1. That's the issue. Maybe you have to take Q to be Q plus 1. Yeah, that's okay. Yeah, that's the one. So yeah, so it's just that, yeah, right. So Q is Q plus 1. So the weight I was putting here. So here Q equals 3. That's it. The valence is Q plus 1. So then if you do it like that, literally, I think you get this. So this is Q to the minus n. So this to the right-hand side, this is harmonic. But there is an issue that on the left-hand side, we cannot just extend it like that. We could. And it would be harmonic. But it would not be bounded. So there is an additional trick that you have to do on the left-hand side to make sure that this is bounded. Right? Because, I mean, we could extend it like that, right? So this could be Q squared, Q cubed, This would be perfectly fine and harmonic. But this would not be bounded.
Just like one.
Do it again?
Well, like exactly the same thing as the one. Then they have one on the
One on the right.
Like exactly the same piece. Then at the origin of like what 4 ones, and the origin is also 1. Is that one?
So what? So you want to put the ones here?
Yeah, and then you just copy the rest.
But where do you get here? Like,
1 is 1, right? You average over the 4 things is 2.
yes. But you see, this is 1 and 1, and this is not quite. Yeah. Well, this is good exercise. Think about it. I'll tell you next time how to do it. You have to modify a little bit on the left hand side. Okay, let's stop here. But yeah, think about it. I think is really is a cool example that.
It's like the next left point by the p-value thing. So you determine what the next point is to left.
Yeah, correct. There is a wait. So what do you know? Well, you don't know everything. You know this one from this thing. You know this one, but then you don't know what these ones are. So the thing is, you have 2 degrees of freedom, not just 1 degree. And that's why you can do it. Yes. Okay, anyways, so think about it. I'll see you on Thursday. So we have also 2 hours.